Welcome to week 2 of Foundations with Algorithms. Thank you so much for being here at our morning time and staying with us for this long lecture. So we're going to start with actually a little activity that we're going to call a minds-on activity. So this is just going to be a quick way to get you guys back into the habit of thinking about algorithms. So we're going to be doing something called a 3, 2, 1. So everyone, we're going to take 10 minutes to do this activity. In the first 30 seconds, we are going to write down 3 ideas we remember from last lecture. Anything that comes to the top of your mind, whether it's about algorithms, whether it's about what the course is about, whether it's about specific topics. I want you to write 3 of them down for me. And then you're going to pair up with the student beside you and pick 2 of your ideas between the 6 that you have that you think are the most important from your list. And then each of you will share 1 idea on that poll everywhere. So you're writing down 3 now, you're sharing with a buddy next to you, and then you are going to put it up on the poll everywhere. Can everyone see and join that? Let me make sure that it's up and running. So I'm going to start a little timer. So get thinking, get writing, think about your ideas. What did you learn last week? What did Dr. Connie go over with you? What do you think stands out in your brain? Okay, I'm seeing a lot of really good stuff here. So how many of you have gone home and tried out the programming exercises already? Yeah? Okay. How many of you are working on your own machine? So not on Ed. You've downloaded your terminal. You've got your code editor. Okay, we've got a lot of people. How many of us are still a little unsure of how to use terminal and how to use all of those things? That's okay. I learned this in 3rd year university and only really understood it in 4th year university. Like it took me a long time to get this. So it's okay to be unsure. It's difficult. It's different and weird. But that's okay. We're going to go over it today as well. Okay, amazing. So I think what we're going to do is we're going to end it there and come back to how we do that in our live demos, and get back into our idea of what exactly we're going to be continuing on with today. All right. So I'm going to close this bad boy down and switch back to our PowerPoint presentation. All right. So something that came up in this is the idea of variables, big O notation. What exactly is happening with different types and different kind of coding conventions and elements of C itself. And so that's kind of where we're going to pick up today. So we're going to talk about types. But not these types, right? Can anyone tell me some types in C that we went over?
My name is Alex. One of the types, integer.
Integers, amazing. Does anyone else have a type in C that they remember? Name first, please.
Darcy, doubles.
Doubles, amazing. Anyone else?
Character types?
Characters? Yeah, character types.
I was going to say characters.
You say characters as well? That's great. There's so many different characters. So we've talked a lot about them. Int, char, double. We're going to get into some other weird ones. Float, long, short, we may have talked about, and eventually void. But don't worry, don't be scared. We will get to what all of these mean. So last week, we talked a lot about integers, right? Does this slide look familiar to everyone? Yeah? Okay, so what exactly did we talk about? Can anyone send me a bit of a reminder or give me an idea of what we're doing with all these clocks? What do these clocks mean to us? Up here in the front. Can I get your name, please?
I'm also Alex.
Alex,
Yep.
Cool.
There's a limit to how much or how far you can count on a computer or how far a computer can count to.
Exactly, amazing that our integers are finite, that we have a limit to them. Does anyone remember what exactly that limit is? It's up on screen for 1 integer, how high it goes. We'll go over here because we haven't had the question answered over here. Can I get your name first, please?
Gabriel.
Gabriel?
2 to the power of 31.
To the power of 31. It actually goes up to 2 to the 32 minus 1. But yes, 2 to the 31 is what we have up there. and then the little clock's up to 0. Beautiful. Okay, so I think we're all getting the hang of integers. Why do we have multiple clocks? We got a question, we got one in the back there. Sorry, I'm gonna be doing a lot of running as we recap, just to get everyone up to speed.
The reason we have multiple clocks for one number is that if we wanted to store a very, very, very large number that was greater than 2 to the 32 minus 1, then we can sacrifice a little bit of precision and simply multiply multiple integers together to specify in more less precise terms a very, 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 very large number.
Exactly. I love your Pikmin shirt. So yes, we had the idea that if one integer could be represented by one clock, well, could we put these big numbers or these bigger integers together by having multiple integer variables that can kind of handle the idea of the ones column or the tens column or the hundreds column? So one of the things we noticed about this, though, right, is that all of these integers right now are only positive. So to recap, we also talked about the idea of 2's complement. The idea that what do we do when we have negative numbers? So what did we do with that? It's up on screen. Anyone remember this?
Names and kids. So what we did with the 2's complement was obviously going from 0 to, I guess, 2 to the 16 or somewhere in the middle. We're counting from 0 all the way to, I guess, half of the large number, and then going the other way. So going from 2 to 31, counting backwards, we're counting in terms of negatives. So -1 is.
Amazing. Yes, exactly. So just to repeat that for everyone, that we go, okay, instead of taking that full 2 to the 32 minus 1, what if we cut it in half and say that, well, half of the clock will represent negative numbers and half of the clock will represent positive numbers? This is amazing. You guys are so good. You remember so much. So why do we need to know this? We need to think about this because as we're working with computers, we have finite memory. And so we need to know some of the information that the C programming language will give us and about how the computer works and about how the computer stores that information. So with that, C doesn't give us a heck of a lot in terms of what it'll promise us, but it does give us some things. So specifically, C specification, which is the manual of how it all works and how it's designed, tells us that we can assume that a char, or character type, is going to be at least less than or equal to a short, that shorts are at least as big as a character, that integers are at least as big as a short, and that longs are at least as big as an integer. So why do we say at least? Because really it depends on the individual processor and the implementation of how these are understood. So in terms of the common rules of what we can expect with this, we can expect that a character is at least 256 values in memory. That's that chart that we showed you. We can go up to those areas. Shorts are 2 to the 16 bits. Integers are 2 to the 16 at least, and longs are 2 to the 32. So this is all kind of just basic theoretical foundational stuff we need to start thinking about how do we use these variables with computers. So I'm going to ask everyone for a minute to get a little mathematical with me. And I'm going to apologize to any of the mathematicians out there for the very, very ugly notation that's going to come up. I am a software engineer, not a mathematician. Please forgive me. So if we know that integers are representing whole numbers, what is 1 if it's an integer that is looking at the world of 32-bit integers divided by 2, where 2 is also an integer? Does anyone have any ideas? We're going to try to think about what will the computer think about this question when it sees this? Yeah.
Hello. Hello. Yeah. My name is Xia, and the computer will give you 0.
The computer will give you 0. Why do you think it'll give you 0?
Because that was the first error I encountered when I was working with C.
That's the first error you encountered when working with C? Amazing. Okay. Should we try it out? Should we do our first live demo of the day? All right. So let's not get scared, everyone. Can everyone see this screen? Do I need to make things a little bit bigger? I can increase the size. I don't use an integrated development environment. I'm sorry. It was broken out of me by my undergrad teachers. You should use them. They are wonderful. But I am going to be coding on my machine using very simple things. A text editor. How many of you guys have Notepad on your computer? Yeah, Notepad. I'm using something called Sublime Text. It's just a text editor. I just type text in it. I will note very specifically that Word, in this case, is not a text editor. It is a word processor. That's why when you make a Word file, it comes out .docx or .doc. We're going to be making something that writes plain text here. So I make it in a text file, and I do it on the terminal. So let's start by making a little file. So I'm going to need a C file, and I am going to get it to do that math equation for us. That integer 1 divided by integer 2, what does it give us? So I'm going to say, I first need to hashtag include stdio, which means for standard input output. That is basically a header file or a library where we get all of those printf, scanf commands. And I'm going to go int main, int argc, char star argv. Don't worry about that. We'll get to what that means later. This is just how we understand to start writing a C program because it'll give us kind of that most flexibility to it. And what am I missing here right now? I need a return statement, and I'm going to return 0. So this is just the start. I'm just going to start, and what should we call it? Let's call it integer division dot C. Oh, wow. My text editor made it really pretty. It doesn't have to do that. It all works the same. So if I need 2 integers, can anyone remind me, how do I make an integer in C code? Has anyone tried? You write the type in front of the variable. That's right. So we're looking at integers. And let's talk n and m. I know they're ugly. I'm sorry. So let's say that n equals 1 and m equals 2, which was our question, right? And so now we are going to print a statement that says the result of some integer. That's all this hash d, or sorry, this percentage d means is that we're going to tell it that an integer goes there, and some other integer is a third integer, because with integer math, we need to make sure that we are outputting the same input. So the first one we're putting in is n, then we're putting in n, and then we're going n divided by m. Seems pretty simple. Everyone understand what I wrote there? Can I get some thumbs? We're all good. You're so smart. You guys already got this. Okay, so let's save it. Now I'm going to go over here to my terminal on the right. And well, first, I need to know how to navigate around the terminal, right? So I'm in a folder called teaching, and I don't know if that's where I saved my code. So what do I start by doing? Well, ls, we saw a fun command. Ls tells us what is going on. Well, ls tells us what's in the folder. And so there's another directory called comp10002. So let's go to that directory. And I do that by going cd, which means change directory. I'm going to start typing com, but because there's nothing else with com in my current directory, I can actually hit tab and it'll take me straight there. And now you'll see on the yellow line, I'm in that folder. Okay, let's try that again. LS. Oh, there's a folder for lectures and a folder for recordings. So I'm going to CD into that lectures one again. And oh, there's a code demo. I think that's where I saved it. Oh my gosh, there it is, way at the bottom. Let me, oh, this is hard for you to read, isn't it? All the way at the bottom there. So I'm going to use another little fun function called clear to erase my screen. And let's ls again. So there's int division. So with int division.c, we're going to compile it. Does anyone remember one of the compilers we can use? You know what? I've got an answer over here. I feel like I want all of you mic'd up so that way I can just ask and you can yell it back at me.
GCC.
GCC, amazing. What's your name again?
Tom.
Tom, amazing. Thank you so much, Tom. Okay, so we're going to use GCC to take this text, this C file text that we've written here, and turn it into an executable file or a program that we can run. So GCC, and then we're going to put in the file name we want. So that's intdivision.c. That's the C code GCC is going to run. And then we're going to use this fun flag called -o or -o. That is basically going to let us rename the output of our GCC file. And I'm going to be a little cheeky and just call it intdiv because I like short forms of things. I'm pretty lazy. And so coding, when lazy, means you can usually write better, elegant code. So let's see what happens. It doesn't look like it did anything. Did it do anything? Yeah? We think it did something? All right, let's check. There's now an executable file. There's now a program that we can actually run here in the program. So I'm going to run it using the command // and then the name of our executable, intdiv. And it tells us the result of 1 divided by 2 is 0. So you were right, Sia. We got 0. Anyone know why? Can anyone think of why? We got Tom, we got Alex, we got one in the, we got one up front. I'm sorry, in the back. I'm just gonna, my legs hurt from running sometimes. Can I get your name first?
I'm Elizabeth.
Elizabeth, lovely.
Because you're like it's doing integer division, and so instead of like the result that it gets in this case is 0.5, but to give you an answer, it doesn't do any rounding, it just truncates. So the integer part of that was 0, so it's telling you that it's 0.
Perfect, that's right. So our integers don't do decimals. They don't understand how decimals work in this world of all whole numbers. So we'll come back to this. Are there any other ways that we could handle this instead? If we tried to do something that still used these whole numbers, could we do anything different? We got one all the way in the back.
My name's Anna. You could change the character type to be doubles instead. So you can do double division, which then can give you a decimal answer.
Amazing. Does anyone else have any other ideas of what we could do?
You could cast one of the integers to a float when you do the division.
We could cast one of the integers to a float. We don't know floats yet. We'll get there. So some other ideas that came up with other classes over the years is to go, you know what? It doesn't matter. In our world of integers, there is no proper answer here. This is a bad question. You're a bad programmer and a bad user. Never write this for me. But that doesn't work very well, does it? We need to know how to do basic division. We can leave the answer as a fraction and just output that idea of 1 divided by 2. Hope the user knows what to do. We can give the quotient and a number. We can give just the quotient. That's that whole part. But if it's just the quotient, that's what C does. It just gave us that 0. And that wasn't very helpful. And now someone has also answered, we can cast it. What that means is we can see if we can treat these integers as if they were real numbers, or like in the back, Isla said, we can just use different numbers. What if we don't use integers? What if we use something different? We want decimals, and C goes, you can have decimals if you want them. We call them floats and doubles and even long doubles. And we are going to get into some of the differences between them today. So with that in mind, what is the difference between these things? We have these decimals. When we're working in the real world, how many decimal places can we work to? How many decimals does a regular number have or a real number have? Infinite, an infinite number. If I asked you to recite pi, right? It can go on and on and on, and we can just keep adding numbers to the end. But we just talked about how computers have finite memory space. So to how many decimal places do we think a computer can represent a real number? Does anyone have any ideas? If we don't have infinite space, what are some things we could do? We'll go back to Alex over here.
So just remembering back when we had this very large number, and then we used like some like scientific notation. We used extra bits to sort of trade accuracy for size. We can do that for decimals as well. Like, yeah.
Okay. So yeah, do you want to mute your mic then and just hold on to it, because we'll see if we can try to get people to pass it to each other. Okay, so we could do that. We could use that kind of clock analogy and see about using extra bits to keep representing more and more. But if I give the computer a string of numbers, how does it know where the decimal point is to start with, right? Those are the kind of things we're wondering about. Does anyone have any other ideas on how we could do decimals? Oh, we got a question over here. Can I get your name, please? And then just mute it once you're done.
I'm like that. So I think we can set up another variable to store where the decimal mark is.
Okay, so you mean to have the whole number part as one variable and then the decimal part as another variable?
Yes.
Okay, that's an option, yeah. And then we can, with that, try to figure out how we do those kind of computations. Oh, do you have a question?
Well, it's not a question, but I believe it has something to do with scientific notation, but my memory is failing me at this point.
That's all right. If you want to mute that and hold on to it, we'll ask to pass it around. So there's a variety of things we can do, and there's a variety of things we have to do to figure out how to get around this limitation of finite space. Because whether it's scientific notation, whether it is representing them using different variables, eventually we can't go on infinitely, right? Every one of these bits, every one of these variables is physical memory. It translates to a physical part of the computer's processor and the computer's resources in this way. And so with that, we just can't put that many onto a chip. How many people have seen a processor, like have held one up and held it in your hands? Okay, some of you. I'm going to give you a hint. If you take a look at the size of your laptops, they're not that big. They have to be quite small. In fact, our phones have processors, so they have to be quite small. So we obviously can't put everything in there. So, okay, we're finite. What do we do about it? Well, coming back to this idea of scientific notation and coming back to the idea of C standards and the fact that languages are something that people made up and just decided some conventions and wrote them down and said, this is what we're agreeing to do. C compilers will generally use the IEEE 754 floats. This is just a manual for specifying where you will decide the numbers on the left-hand side of the decimal place are versus the right-hand side of the decimal place. It does have something to do with scientific notation and how to kind of figure that kind of information out. But that being said, that's a lot of theory. Let's see what this means in practice. So we're going to go over to here. And let's first check to see what we can do about solving this integer question. We said the first idea is the idea of using doubles instead. So I can go in here and change this to double. And do we think this will work? If I just go, hey, back at the top where I said these are integers, now I say they're doubles. I'm going to save this code and we're going to run it. How many people, show of hands, think this will work and we're going to have no problems? How many people think, you all think it's going to have problems? Yeah, you all think it's going to have, no, you think it's going to have no problems? You think it will have problems? We got problems, we got problems. Yeah, question. Problems? 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 Oh, yeah, okay. We all think it's going to have problems. Let's see why we're asking you to use the terminal, because I don't have a fancy IDE telling me that there's a warning here or something going wrong. It's just going to let me save this code and try it. So I'm going to save this code. Let me clear so everyone can see up at the top. We're good. I'm going to teach you another pro gamer move here. In your terminal, for a lot of you, if you just press the up arrow, it'll go through all the previous commands that you've run. So I'm not going to type out GCC again. I'm just going to press the up arrow and get to it. Okay, 1, 2, 3. It ran. Why did it run? Actually, that's a really good question. Why did it run? The result of 0 divided by 0 is 0. It doesn't know what it's outputting. It did the math, but there's something here. Let's try instead using a different flag. This is one you're going to see on ed. We're going to say dash capital W all. What that stands is for show me all warnings. Oh my gosh, that's a lot of warnings. That's a lot of warnings. What is it telling me to do? How do I read this? Let me open it up real big here. So it's telling me that this percentage %d expects that it's going to get an integer, and instead it's getting a double. So what am I supposed to do instead? Well, it actually tells me as well that I need to replace that with the percentage sign in F for float. Or more specifically, we're going to use LF for long float. That's going to give us more precision with that double. But the reason I did this and was surprised that GCC didn't tell me I couldn't is because I wanted to show you all how to use the terminal for debugging. Because you're going to run into errors in your code all the time, and that is okay. 99% of programming is actually learning how to read your errors and figure out where to go from there. So when you see this, your program actually tells you, or the compiler tells you, which file there's an error in. So int division.c has an error. And then the next number after that is your line number. So on line number 9, and then the column number, and that's column number 43. So if we go back into our code here, line number 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're going to go over column 1. Okay. 40. So the first one up top actually says 32. And 32 is over here at the end of the thing. So we have this error here that says it's expecting an integer. It's not an integer. Another pro tip, when you are debugging, you will sometimes get lots of errors or lots of warnings. Always start from the top, because that first error might be the thing causing all the subsequent errors. So don't start at the bottom like I did right now. That's bad practice. Start up top. Okay, so we're going to instead switch these to LF and run it one more time. And there we go. The result of 1 divided by 2 is 0.5. That's what we expect. Now, I'm actually going to do something different. We're going to take a look on my computer to see exactly where this floating point issue comes up. So we're going to start again. We need to output things. Can anyone yell out to me? What do we start with? If I say hashtag include and I know I need to output something, what goes in these brackets here? Just shout it out. STDIO, standard input output. Okay. And then we're going to start with our int function, int main, int argc, car star arg v. We're going to get to what that means at another time. Return 0. And we'll get to what that means. Okay. And so now I'm going to have some doubles, x, y, and z. And let's say x is equal to 0.1. Seems like a good number to start with, right? I want to see how much decimal place space that 0.1 actually is precise to. And let's just start adding up some x's, right? 0.1 plus 0.1 plus 0.1 until we get to, what, should we say 0.5? Let's see if it can get to 0.5 accurately. So y is x plus 2, 3, 4, 5. So we're expecting here that this is going to be 0.1, and we're expecting here that this is going to be 0.5. I'm just going to save it for now, and we're going to save it as rounding. Okay. And now let's do this. If we know that y is supposed to be 0.5, right? What if we make z y minus 0.5, right? Then it should be 0. Sound good? And now let's print these out and see what they actually are. So x is equal to, and we are going to say a float, but let's be a little more precise. We saw in our last float, it only gave me like, what, 6 digits past that decimal place? I want to see far. I want to see real far. So let's try instead maybe yeah, let's try that. And let's try then and we're going to say y is equal to, and we'll do the same thing there. All of these numbers that I'm just putting in front of the float is just basically a way to say, show me this many decimal places. We'll change it up and I'll show you after. But basically, I want to just make sure that we have enough decimal places that we can see this in action. All right. And now in my print statement, I need to tell it that the first one should be x, the second one should be y, and the third one should be z. And I'm going to need my semicolon at the end. Otherwise, it's not going to compile, right? So let's save that. GCC. This one is called rounding.c. And we're going to call it rounding. And let's see what it does. Whoa. So funnily enough, to that precision, we see that x does not actually equal just 0.1. It's 0.1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, blah, 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 555. But we do see that at that level of adding it all up, the precision didn't actually matter with y, and then z came out fine. So the reason that we show you this and the reason that you should pay attention to this idea is because some of you, especially when you're working with super specific numbers, if you're ever going to be doing a program for a chemistry lab or for something in data science or for something where you need to be really, really precise with these values, things like that might come up. How many of you have taken a high school physics course? How many of you have done those kind of experiments with a stopwatch where you're sitting there trying to record your own reaction time? Yeah, and you see, I can't press it perfectly at 0.1 second. Neither can the computer. It might be better than me, but it's not better than everything. It's not better than our theoretical math. Okay. So, rolling back into here, That was our live code. So just to wrap that up, C has floats, doubles, long doubles. Why do we use different ones? Why did we use a double here? The reason being precision. So floats use only up to 32 bits, so they're only so precise. A double says, to heck with it. Let's use the full 64 that we can, baby. I want to be as precise as possible. And then we can even have long double floats. The moral of the story is, for your code, I highly recommend using doubles, especially in this class, because that's where we're going to get the most precision and accuracy. There may be some cases where you're going to use floats for different things, and you may even encounter in the future when you're working with other libraries or you're adding to programs that somebody else wrote, you might find that somewhere there you will encounter floats and have to use them then. But highly recommend start with doubles. Let's start working with doubles. Any questions so far? No, we get it? We're still finite. We're still working in this limited space area. So let's go back to our question before when we had these integers. And I put up some possible solutions that came up previously. And specifically, this one. We can answer as if they were real numbers in Python. What if, we just pretended that the integers were real numbers and had those decimal places? So we already handled the suggestion of Isla in the back that we change the actual types to doubles. And now we're going to address something that was brought up here by Tom. Tom, thank you, Tom. This question of, can we get C to pretend for a little bit like these integers are actually decimal places, like these integers actually have that kind of scope? So with that, I introduce you to the concept of typecasting, where, like a wizard, we are going to go through this process of transmuting to some effect the type of one variable to another, but only temporarily. So to cast a variable, what we actually need to do is tell the computer what type it should pretend it is. So I'm going to go back to our integer division code here. Oh gosh, I've put it away. Let me just open that up real quick. So we had our integer division code here, and it was previously just integers, right? What I could do instead, let me make a double that we're going to call Z. And we're going to say instead that Z is equal to N divided by, and now we're going to cast M. This is where the magic happens, people. We are going to tell C that instead of this integer, I want you to be a double, and I want that double to be M. And then I'm going to change this back here. That. Okay, so we have now cast our magic spell. Let's see if C will like this. I'm going to call it intdiv cast. So even though I've changed the code here, that means I'm going to have my old program where it was just those doubles as well as intdiv. So now intdiv cast. Let's see if intdiv cast works. So now we can see that the result of 1 divided by 2 is 0.5. So that is a concept that we call explicit casting, where we are explicitly telling the computer what type to treat this as. And particularly with that you are not creating a whole new variable, that just temporarily, just for this one statement, pretend this is another number, or pretend this is another type. Can anyone think, if I have an explicit cast, we tend to like to work in binaries or twos here. If I have an explicit cast, do we think I can have an implicit cast? Yeah? No? Yeah? All right. How do we do that? If we have this idea of an implicit cast, what can we do? Well, let's say instead of int, we'll have int n. Let's say that m is a double. 2.0. Now we know that z is supposed to be a double, but now we have an integer divided by a double, right? In theory, does that work? In fact, I realize I have a slide for this. Can we do that? We love types in C. We want to be strongly typed in C. So we want to work only with the same types that we have, which never really happens. You might not work with what type you actually have. Can I do this? So let's change m to 2.5 just to match our slides. And let's save there. And I have not paid for Sublime Text. I use the free version like everyone else. I'm sorry, everyone. I'm just like one of you. Okay, let's try this again. Now, oh, can anyone tell me what I did wrong here that GCC didn't tell me I was doing wrong? Why did I get this result of 1 divided by 0 is 0.4? Yeah, we got an answer over here. Tom, if you could pass up the mic, please, that would be lovely.
You didn't change the percentage D to LF.
Amazing. I didn't change that second D to a float. Let's try that again, shall we? There we go. 1 divided by 2.5 is 0.4. Okay. So we can do this thing called implicit casting or type conversion, where we know even if that's an int in n divided by a double, it'll go, I assume we'll treat the int like a double. I will force us to pretend the int is a double. I am implicitly going to assume the int is a double. Okay. Cool beans. So why do we bring this up? Because it's a trap. It's a trap that everyone falls into at some point. Types are super, super important in C. In fact, in all of your classical object-oriented languages, classes and types are everywhere. You'll have run into them in Python, you'll have run into them in C. For those of you who will do C# or Java, there are types everywhere. But it's super, super easy to forget how they work with each other, to mess them up, to misuse or even abuse them. I have been known to abuse type theory and certain things too often, and that is bad practice, and that makes my code smell a little funky and fishy, which is just a term we use to mean that it doesn't look like a good, elegant program here. So please keep it in mind as you're looking at your own work and as you're working through things. So, as we kind of wrap up this little last section on the beginning of types and working together with them to do arithmetic and do some basic computation in C, we want to talk about operators. Everyone here has taken a math course, right? Can anyone tell me a fun little acronym for the order of operations if I'm looking at a function? If I'm looking at a math equation, how do I know which parts to do first and then which parts to do second? I can't hear you guys in the back there. You gotta yell for me, please. BODMAS. I'm from North America. I'm from Canada. We use BEDMAS, but BEDMAS, BODMAS, all the same. And we know how to do that. And how many of you have gotten stuck in those Facebook arguments with people where they put out a question and they're like, why do some of us get 5 and other of us get 6? Because there aren't clear brackets. There aren't clear BODMAS rules, right? It's frustrating. You go, this is unclear. I got a question in the back. Sorry, can I ask someone to please hand a mic up there? Yeah, if you want to run up, please.
Okay, this isn't really a question.
Yeah.
Just but to build on the point, there is actually, I think there is a standard where it mentions that. Hang on, remember,
yeah, keep going, keep going.
I know the SI approach which specifies how to write say metric units.
Yeah.
Actually said actually says that if you do say, and also many things for physics, chemistry say, if you write A, you cannot write A/B/C. You have to put brackets.
So this is a weirdly fun thing, and this is an aside. I'm so sorry, everyone. You've triggered one of my pet interests. This is not part of your tested material. This is just something I'm going to tell you. So a lot of computer science and a lot of computer scientists started as mathematicians. It's kind of the applied version of math. In the same way that engineering is the applied version of a lot of sciences, computer science in some ways is theoretically derived from math. That being said, that meant that a lot of the people I was taught with were mathematicians first, computer scientists second. And this is a big argument in computer science research versus math research, because in math research and in math theoretically and generally, there are these standard conventions that are predominantly based around English. This idea that if there are no brackets, if there is no existing precedence, you are meant to read the equation left to right and then kind of operate that way. And computer scientists hate it. They got so mad. And there's a whole theory of math. In fact, my supervisor for my PhD, this is like one of his areas of work, is like type theory and calculus in computer science, because they're like, computers are not smart enough to understand what a convention is, guys. Computers, as many of us like to think are smart, they're dumb. They're so dumb. They're only as smart as the person who's programming them. And even then, we have so much ambiguity in our language. We have so much ambiguity in our math that we just go, everyone will know to read from left to right. That's what we'll teach them in school. It's what we'll all do. Computers don't know that. And so because of that, computer scientists and math are in a little bit of a feud about like the theory of this. So thank you for that statement and that idea, because I want to wrap this all back to what we're talking about. What is the operator convention and the precedence order for computers? So I'm not going to ask you to know this off the top of your head. I'm not going to ask you to memorize this even, but it is something to be familiar with, because as we go through, we are going to end up writing long logical statements that are going to have multiple operators in them, and we need to know how they evaluate. So in order of precedence, the first thing that happens is any kind of incrementation or decrementation. That takes the top precedence, so that's the highest, all the way down to the bottom, which are these kind of assignment and then logical comparator elements here, or different types of assignments, which are the lowest precedence. So this is something to think about and know. How many of you all have seen these operators before in your own work? Yeah, we should have seen some of these. Some of them are logical, like our and or statements, which will give us some kind of binary logic or some kind of truth table, so Boolean logic, as well as our comparators. And then some of them are just obvious in terms of like addition, multiplication. But some of you might not have seen this operator. Can anyone tell me? We saw this in our text, but it's not the same, unfortunately. When we see this in math, does anyone know what this is? Alex, can I ask you to pass it up front, please?
So it's like division, but you ignore the what's the name? Well, you ignore the what's left.
You ignore the quotient. You want to check the remainder.
Yeah.
Yeah. So if everyone remembers, when you're doing division, the quotient is the whole number, the number of times that it goes into it, and then the remainder is what's left over that doesn't go in a whole number of times. A lot of us might have forgotten that once we figured out decimals, but back in like grade 3, you would have learned about this idea of saying it has a remainder. And so that's where our modulo operator or modulus operator comes from. It's this idea of doing math based on the idea of a remainder. We'll see it in our clock arithmetic. So when we go, our clock starts at 12 noon and it goes all the way around. And then once we kind of hit it, what is 13 o'clock? Does anyone know what 13 o'clock is in regular 12 hours? You just yell it to me. 1, right? That's wrapped around. We've done 1 revolution of 12, and then we have a remainder of 1. So there's kind of our modulus idea. And we're going to use it to be able to understand some kind of other properties of data when we're solving problems later. So some common order of operation pitfalls just to think about. In most languages, Our logical operators of and or are evaluated left to right and terminate once the answer is known. What does that mean? That means if I say this and that, when I'm normally thinking about it and translating to that Boolean logic, and is only true when both are true. If one of them is false, then the whole and statement is false. Has anyone encountered Boolean logic before? I don't know what you all have taken. Yeah, if you've seen Boolean logic, put your hand up. Okay, very cool. Love this. So yeah, so ands evaluate to true only if both sides of it are true. Now, if I'm in C and I check the one on the left and it's false, I'm not going to bother. I'm lazy. I'm not going to bother checking the other part of it. What does it matter? One of them's already false. So this is where that idea of understanding how it operates works, how it moves left to right. Similarly, can anyone tell me when is or true? Yeah, we've got one over here. Sorry, Gabriel, can I borrow that microphone, please? Or can we pass it down back over here? The one in the lovely pineapple shirt. Can I get your name too, please?
Yeah. My name's Lottie, and an or is true if either of them is true. So if the left expression is true, then you're not going to bother with the right because you can already move on.
Amazing, exactly. So why would I do twice the work when I already know the answer's coming up? So remember this, that precedence rules do not specify the entire order. Be aware of the compiler and how it's going to go through and do things. It might not always be obvious. And particularly, precedence only tells you what comes later in the operations, not necessarily what comes earlier. So when you have those things like multiplication, which side of that multiplication is going to happen first before the addition, all of those kind of things. Okay, with that, you all have been such excellent sports. We're going to take a 5-minute break because I know 3 hours is a long time to be sitting. We are going to get started with a little activity. I hope that everyone's ready for this. I'm a games person, and so with that, I thought it would be fun to play a little game called Simon Says. How many people have played Simon Says before? Okay. Some of you haven't. So the way that Simon Says works is that I will be Simon. I am the person calling out for you what to do. And if I say, Simon says, do something, you have to do it. But if I don't say Simon says, then you can't do it. Otherwise, you're out. Okay? So, for example, could I get a volunteer to the front to kind of demonstrate for people? Who knows how to play Simon Says and can be a volunteer for me real quick? No? Yeah? Come on up. Big round of applause for our volunteers today. I love this. All right. So we're going to do this like a classic thing. So I'm going to get your name again for the audience.
Alex, hello.
Alex, lovely. And Alex, how long have you been playing Simon Says, do you think?
15 years, maybe?
15 years. Do you think that makes you a pro at Simon Says?
Absolutely not.
Absolutely not. All right. Well, we're going to do a little demo for everyone in the class who'll be playing with us in a sec. All right. We can put our mic down. So if I say, Alex, Simon says, put your left arm up, then the left arm goes up. And if I say, Simon says, put your left arm down, and Simon says, put your left arm up, and put your right arm up, bravo, excellent. If I don't say Simon says, we don't put our arms up. Okay, so we're gonna do this real quick. Thank you, Alex. We're gonna head back to our seat. And I wanna see full audience participation in this because this is related to the course. I swear to you, all of this. Okay, all right, everyone, ready? So Simon says, right arm up. Okay. Simon says, left arm up. Simon says, both arms down. Simon says, stand up. Simon says, spin around. Left arm up. Oh, I haven't gotten anyone yet. Okay. I didn't say sit back down. All y'all best be standing. Oh, do we have some people out? Okay. Simon says, sit down. Simon says, hands on your head. Simon says, hands on your belly. Simon says, hands on your head again. Belly. Oh, I almost got some of you. Okay. All right. Simon says we can put ourselves down. So, why did we do that? What is the purpose of getting you all to play Simon Says? Yeah. Do you have a question or a comment or an answer to my rhetorical? Answer, yeah. Let's grab a mic to the back. In the middle, striped shirt.
To illustrate how computers work. Basically, they're like very obedient servants. They will only do precisely what you tell them to do.
To illustrate how computers work. Excellent. In fact, it's particularly to illustrate something that you might not have heard about yet, but if you have, please bear with me. The idea that C is an imperative language. How many of you have heard that term before? Imperative language or an imperative program or imperative paradigm? No? That's totally cool. So imperative basically means exactly what our friend here said, which is that the computer does exactly what I tell it to do. I am sitting here with commands telling the computer X is 5, or add those two numbers together, or return this value. And the computer will do it as I say it in order. Most of the languages that you are going to encounter in your undergrad are probably also part of this imperative paradigm, where you are going through and telling the computer exactly what to do. There is another paradigm called declarative programming, where you tell the computer kind of what generally you want it to do, and it'll figure itself out how to do that. We're not going to deal with that. That's a problem for like a third or fourth year functional programming course. That's not a problem for us right now in Foundations of Algorithms. And to be fair, that's not a problem many of you will face when you go out into the world to write programs and do things. So, if computers are kind of dumb and need to do exactly what we tell them to do, we need to figure out a way where we aren't constantly having to tell it every time the same thing over and over again, right? Because that's a pain. And I can't talk that long. Well, that's a lie. I can talk that long, but not everyone here can. And half the time, I don't want to repeat myself. So this is where we need to know how to use different control structures for the programs to organize their logic and organize the flow of data and information through the program and through our code. And what that's going to do is help us say, let me give you some instructions, and you, the computer, should be able to figure out for yourself by following my beautiful recipe step by step how to make this for yourself. So to get started with that, I'm going to give us a bit of a puzzle. So I'm really, really bad at time. That's my problem. And sometimes I want to know how many days are in this month that we're in. How would you all figure out how many days are in the month? We've already had some answers over there. What do you think? Days in the month. Anyone have an idea? Otherwise, I'm going to start calling on people randomly. And I see we're making eye contact, but because of that, I'll be kind and then not particularly pick on you. But yeah, we've got an answer in the middle here. If you wouldn't mind, Aditya, thank you. How many days would I figure out's in a month?
Hello. Yeah. So I use my name is Hitat. Yeah, and I use the knuckles method.
Oh, the knuckles one. I've heard of this before. Can you show us how that works?
Yeah. So the first knuckle is January, so that's 31 days, and then it dips, so that's February, and at each knuckle it's going to be 31 days, and then you take the other hand. So July will be the last one, so that's July is 31, and then August will be 31, and then it dips. Then October is 31, and then December is 31.
Amazing. So that's one way. Thank you. Does anyone have any other ways? Did anyone learn any rhymes or anything like that? You just look at the calendar. Gosh, I wish, but I will let you know. I don't have a calendar on me most of the time. I thought I saw a hand over on this side. Did anyone have any idea over here? Oh, someone stole your answer. That happens. Has anyone ever heard of this kindergarten rhyme? 30 days has September, April, June, and November. All the rest have, except for, okay. So we have some information here, right? We know, everyone, that there are 3 types of outputs, 3 numbers of days that we could have in this calendar, right? Either months are 30, 31, or 28. That gives us an idea of the first control structure that we can actually work with here, something called an if-else statement. So I know that many of you took Foundations of Computing last year, so you probably know what an if-else structure is, right? So can someone explain to me what an if-else structure is? We're going to start going over, let's see. I'm going to pick on, I'm going to pick over here. Do you want to answer it? Yeah. So name and.
My name is Thriti, and so in an if-else structure, we have 2 statements. So if this happens, then do that, and else we do something else.
Amazing. So we have if something is true or if we are doing something, we'll do some set of code, and else we will do something else. You may have even seen in Python previously the idea of elif, or what we will use here in C is else if, for if you have multiple conditions that you need to meet. So notably, what we are going to do now is do some little bit of C coding to get an idea of what this looks like in our actual structure. So switch us back here. So let's make a new file. And I'm going to say we want to take in some input from us to tell me what month am I thinking of, right? So I'm going to start with our basic main structure. Car star RV. I'm just going to save this for now, and we'll call it months.c. So I'm going to write out over here a little bit of comments to explain what we want to do, right? So we want to get the user to input a month. And right now, let's leave it with numbers. We have 12 months. We can do it. And let's say the format should be 2, right? And then after we do that, we want to check how many days are in the month. And we want to output or print to the screen how many days. Seems simple enough. Any problem we have in this course, we're going to break down by thinking about what are the steps in this problem. And then we're going to go through and try to do it. Okay, so let's start with the idea of taking in something from the user. So we know that our months are coming in this format. What do we know about months that can help us understand what type we should be expecting? They're whole numbers. Amazing. Months are whole numbers. And so if we're dealing with whole numbers, we are dealing with an int, right? So we're going to say there's an int, and we want to take it in from the user. So we're going to need to tell the user what to put in first. So we're going to say printf, and this is good user experience programming, kind of my wheelhouse. You don't want to give them a blank line with no information. So we're going to tell them, please input a month in the format. And now what are we going to do? Well, we've told them what to do. We need to read it in from the screen, or we need to read it in from the terminal. So here we're going to use our scanf function that's going to take in inputs. I don't No, I don't think we've talked about scanf yet today. Have we all seen scanf last class? Yeah? We understand how that works. Just in case we don't, scanf is going to scan for any input from the actual terminal line itself. Scanf will only go to that first input and then white space. So unless we tell it that it has multiple inputs coming in, it's going to stop at the one. So we're going to just right now only take in one, so that's fine. So when we're doing scanf, we have to tell it what kind of structure to assume that it's going to see. So it's going to see an integer, just one, right? Because we're just doing this. And the fact that it's 2 digits doesn't matter. It's still one integer variable. And now we have to tell scanf where to put it. So for this, you will have seen this very interesting ampersand, which basically means address of, but we will get to it not this class, but next class, exactly what that means. So for now, just hold it in your mind. I know when I'm scanning F, I need to give it the ampersand, and I need to tell it where that actual variable is. Okay, so we now have gotten a month from the user. So now we have to actually check how many days are in that month. And we can do this using our if-else structure, right? So, well, let's start. If our month is equal to 01, which is January, we know that it has 31 days, right? Okay, cool. Else, if our month is February, we can go printf. How many months is February? 28. Okay, we're getting somewhere. But God, how many months are there again? 12? I don't want to have to write out 12 of these. This is awful. Can anyone think of a better way for us to do this? Knowing our lines, knowing our little knuckle trick and our poems. I'm gonna go, ooh, we got someone new in the back. We'll just get a mic to you real quick, just because you're just far enough that I want to make sure people on the left here can hear it. And can we get your name first, please? I'm still trying to learn everyone's names. I'm sorry. I'm not as good as Dr. Coney.
Yeah, I'm Kavya. A simple way to do this would be using the modulus statement with mod 2. So if we get mod 2 is equal to 0, that means there's no remainder, means the month is even. And if we get mod 2 is equal to 1, that means the month is odd. And that way we can.
Okay, let's give that a try out and see if this works. So what you're suggesting is to instead go if m modulus 2 is equal to 0, which means it's an even month because there's no remainder. Then we're going to print which one? The even months have how many days? 30. Okay, print 30 days. Okay. And now we're saying else, because if it has any remainder, then we're saying it's 31. Now, we're gonna try to run this, but I'm thinking there might be something we haven't thought about here. Let's try GCC, and this is months.c, months. Okay, let's try to run it. Okay, let's please input a month. So what's this month? March. March is which number? 3? Let's put that in. How many days? Somebody look up on this thing you call a calendar? Calendar? Am I saying that right? How many days are in March? 31. Okay, so it looks like it's working well right now. Can anyone give me another number? Oh, we got a comment here. Can I get, let me get you a microphone real quick. Thank you, Drithy.
I was gonna say, you want to try August?
Do we want to try August? Yeah. So August is number 8.
Yep.
Right? August has 30 days. Does that seem right?
Nah.
That's kind of off. We said, let's see, let's knuckles January, February, March, April, May, June, July. Oh, August is supposed to have 31. This was a good attempt, though. We got to the good point. So now we have certain exceptions. August. Can anyone think of another exception that we would have? February, I heard someone say, because February is an even month, but it only has how many days? 28, right? So this is a good try. Let's try something else now. So can anyone else think of a way, instead of me having to write out every single month, that maybe we can use our precedence information to tell us how we can write things? Maybe we can write something big. Do you want to answer again?
Sure.
You got the mic?
Why not? I mean, you could categorize it as either 30 days, 31 days, and then else 28.
Okay, yeah. So let's before I do this, let's see. Does it have 30 days? Does it have 31 days? Or the special exception, does it have 28 days? All right. Now that's a good way to categorize it. That's the way our poem categorizes it. That's the way our knuckles categorize it. How can we write that? Well, let's see. If our month, let's start by this. Which months have 30 days? 30 days has September, April, June, and November. So that's 04 for April, 09 for September, 06 for June. Let me write them in order, and 11. And the rest have 31. Only one has 28. Which one has 28? February. So that's 02. So now maybe we can use this information to create a much more elegant form of an if structure here. So let's see, if month is equal to 4, or that month is equal to 6, or that month is equal to 9, or that month is equal to 11. So it's either April, June, September, November. Then we're going to say printf, this month has 30 days. Else if, now here we know all the rest have 31. All the rest sounds like an else statement to me. So let's put that at the end. So we're going to check. Does it have 30 days? Is it either one of these? Else if it's February, then we're going to print 28 days. And now we can use our lovely else statement because we've covered all of the months then, right? We've got all of those integers from 4, 6, 9, 11, and every other integer is going to have 31 days. I accidentally hit insert, didn't I? Insert. Yeah, okay. 31 days. Okay. Now let's try this. Save. Control S, our favorite friend. Oh, I got an error. What do I have here? 09 in octal constant. What did I do? You know what? 04 doesn't make sense. 09, all of that doesn't make sense. I actually need to just put in 4, 6, and 9, don't I? We're learning on the fly, everyone. Thank you for coming to this class. All right, let's see if that fixes it. Okay, seems to have fixed it. Let's go back to our top, and we're running months. So let's put in a month in the format. Let's try again 03 for March. March has 31 days. What was the other edge case we talked about? August. Let's try that. August has 31 days. And February has 28. Okay. So now we've got an idea on how to actually do this. Now, that first little bit where we were typing everything out, that's really funky. If you do that in your code, that's called special casing, where every single condition has its own like if statement here. Generally, if we see a lot of special casing, it's a little suspicious in code. The reason being is you're kind of brute forcing it. You haven't thought elegantly, you haven't really thought about the problem too much beforehand. Sometimes it's really necessary. Like in our case here, it didn't make sense for me to do this in any other way. We had these 3 cases. That's fine. But if you're writing out if m equals 01, if m equals 02, and you're starting to see a lot of repetition, that's usually a sign that Your code's a little ugly. Your code's a little fishy. It's fine to start that way, but really think about it and really think about how can I do this in a nicer, prettier way. With that though, we notice some fun, funky issues here, right? February, is it always 28 days? No. When is February not 28 days? Leap years! Leap years! Amazing! So now we got to figure out how the heck do we do this for leap years? Because I'm not checking this so-called calendar idea. That seems like a lot of effort for me. I'd have to go to a store and get one. Awful. So let's change our code to see how we can do this. Does anyone remember what are the qualities of a leap year? When does a leap year happen? Every 4 years. We got that up front. Thank you. So we need to now, I think, check beyond our months. We need to check what year it is to figure out what's going on there. So let's add a new integer, year. I'll put 4 in there. It doesn't need to be 2 M's or 4 Y's. That's just for readability. It's really important when you're writing your code to try to be literate, is the word we tend to use. But really it means making sure that your variables indicate or describe what they're supposed to be talking about. So when we think about years, we can have years in 2-digit formats like 98, 10, whatever. Or we can have those 4-digit formats. And so we're going to want the 4-digit. That's why I'm using those 4 Y's as a variable here. So now we're going to say, please input, we have a month in that, but let's say month and year in the MM/YYYY format. Now we want to know with scanf, let me hide the mini map on the code on the side. Can we all see this? Is this all good? Okay. So now with scanf, I want to know, are we getting in 2 variables? How do we do that? Well, we can tell scanf to expect 2 variables. So when it sees a particular type of input, to know that you separate them this way. So we're going to tell scanf it's supposed to get an integer, first, and then it should see a slash, because that's the format we asked them to use. And then it's going to get another integer. And that integer is going to be our YYY value, YYYY. So, do we have a question in the back? Sorry, can I get you, Tom, to run the microphone up to, I want to say other Tom? Tim. Tom and Tim. Pickman, Tim, and then Tom. Got it.
So my question is, since we've specified MMYYYY,
Yeah.
At the way that it's written right now, even if they just put, if they put like 07, I'm assuming it would know how to handle that.
Yep.
But what if they, they were dyslexic and they put in YYYY and then
the other way? That's an excellent
how do we
question.
enforce the fact that they have done the right thing?
That's an excellent question. Let's actually get into that a little bit. So what we're talking about here is the concept of value checking or input checking to make sure that what we're getting is valid. So one of the things we can do to do that is to start by just going, well, what if they only put in 1 input? I asked them for the month and the year. What if they still just put in the month? Scanf can do that itself. So scanf is a function that actually returns a number. Everything in C is technically a function that returns some value. So with scanf, what it returns is the number of pieces of input that it has read. So we can start by saying if scanf, which will do that operation, it'll put those inputs into those values, and we want it to say does not equal 2, because here we want to check that they've done exactly 2 inputs first before we get to did they put them in the right spot? Did they put in 2 generally? Let's delete the that. So if it's not equal to 2, then let's exit out. Let's tell them they made a mistake, right? So we're going to then say printf missing variable input. And now we are going to exit our program. So often when we are exiting a program, we are doing so from, because we're running them in the terminal or in the shell, we're exiting back to the shell. So we want to pass it some kind of values to say, this is exited with an error. In old-timey ways, we used to go return -1 for error. That is such an old-timey thing because it's not necessarily interpretable on every terminal or every computer that that's what that's supposed to mean. It's another convention, kind of like that whole reading left to right thing. So instead, what there are several exit functions and exit defined variables, which we will get to later. But just to make it a little easier for us, I'm going to go include standard lib.h, which is the standard library of functions. You might eventually encounter this, and I'm going to exit it with a 1, where I'm just going to use 1 to mean that there was an error here. So I know it's kind of old, it's not kind of pretty, but we'll do that for now. So that's the first thing we can do is if they don't have that, then we need to exit right away. Now we want to check that those functions are actually correct, right? So now that we have those, we know that they've entered 2 and they've entered them into those variables, we want to check Tim's question of what if they put the year in the month column and the month in the year column? Now, there's a couple ways we can handle that. Because first, before we think about even checking it, we want to know what do we want to do with that information? Do we want to go through and fix it for them? Do we want to assume, hey, we know you meant it the other way, we can fix it for you? Or do we want to go, no, start again? I think for now, for the stage that we're at, we're just going to say no, run the program again, start again. So we can do this by using our if conditions as well. So let's start. If we know that the month must be between which numbers? 1 and 12, perfect. So if month is less than or equal to 12, and month is greater than, strictly greater than 0. We can flip them around, doesn't matter. Because both hold true, but we need to use an and, which means we need to separate them out. So I'll flip them around for readability. So the month must be bigger than 0. We don't have a 0 month. That's fine, that's why it's strictly greater. The month must be less than or equal to 12 because it can be anywhere from 1 up to 12, but we want no higher. We got a question over here.
Yeah, so get rid of the and just put it as in it's greater than 0 but less than 12.
Not in C. C is silly. You want to separate those out logically. Because if you do, we can try it and we'll see if C runs, but the math person in me goes, you should be able to do that. It's obvious, but computers are dumb. So I might be the only computer science teacher who will tell you that computers are dumb, but they are. So if it's between that and that, then we want it to run. So actually, what we want to do instead is exit the program. So if if it's not in that bounds, we want it to exit. Let's use our BODMIS rules. Let's do some operations here, right? So instead, what if I say evaluate that and to see if it's in between there. And if it's a good number, that should be true, but I don't want it to be true. I want this to be not that. So if we are not between these numbers, where that exclamation point means not, then we're going to say month is not right. And we're going to exit. And we'll give it a different number because the numbers I'm putting in here are virtually meaningless. So we're going to exit with 1. Instead, let's exit this one with a -1 to say that, hey, actually, this is a month error. So that way when the shell comes back and says, hey, I got a -1, I as a programmer can go, oh, -1 means they put in the wrong month. And let's test this now, just in case, because I can also be a bad programmer at times. So let's run it through. So this is months. So GCC months.c months with checking. All right, now let's run months check. So let's please enter a month and year in the format. So let's start by checking that first piece of code. If I just enter a month, if I just go 03, there's a missing variable. It tells us that there is a missing variable, and let's close our program down. Now let's run it again, and this time I'm going to enter let's enter, what's a bad month? 13. 13's not a month, but I'm also going to give it 1994. So it moved through that first check to see what's going on. It says, you've given me a month and a year, and now it's hit that second one, says the month is not right. We can be more descriptive of that. We can tell them after month is not right to months must be between 1 and 12. But that's how we do error checking. Does that answer your question?
Before, when you're printing out,
Yeah.
the format specified how you wanted the number to represent, like how many digits.
Yes.
Is there a more succinct way instead of saying I wanted them to input a two-digit integer or like a
No, unfortunately, the way that it works with the variables is that that integer element is always an integer. That integer can run between that 2 to the 32 minus 1, right? So I'll have to get back to you because there may be libraries that do that, and so I might have functions that are not common to the C standard that I'm forgetting, because I will say I can forget these things. But as far as I think you would often do this. We got a question up here.
You mentioned how the exit function would return whatever number we want.
Yeah.
Or like in the shell, it would tell us that number. How do we see like that shell?
We will get to that at a different time because shell manipulation is a little beyond the scope of what we're talking about right now. But basically, the idea is you can have multiple programs running at the same time. That's all an operating system is multiple programs. And so sometimes one program might rely on another one and be running that way. I'm going to speed us up a little bit just because I realize I'm running a little behind time. But maybe what we'll do is we'll skip a second one. Okay, so we have this. We know that that doesn't work. 28 days is not quite right for February. How can we do this instead? What do we know about leap years? We know that they happen every 4 years. Are there any other conditions for leap years? Oh, we got one in the back over here. Do we have a microphone in the black shirt, please?
So it should be evenly divided by 400 as well.
It should be evenly divided by 400 as well. So every 4 years, every 400 years, there's one more then. What's in common between, what's another factor for?
If it can be divided by 100, it's not an leap year.
Amazing.
Except the fact that it can be divided by 400.
Exactly. Perfect. So yes, our leap years are every 4 years, every 4 years, but not every 100 years or not 400 years. So how can we do this? Well, let's start by thinking about what if we have an integer that says the length of February, because that's what we want to understand. We want to output what that actual number is, not just whether it's a leap year or not, right? How do we check that? Well, February, we know, is going to be equal to at least 28, because it's by default 28, plus 1 if it's a leap year, but not that year being 100 or 400, divisible by 100 or 400. So this is where we're going to do something a little fun and kind of tricky. So give me a moment and then I'll explain it. So we're going to take our year, divide by 4, modulo 4. So this is where our modulo arithmetic comes in. Because if it's a leap year, it must be divisible by 4. So our remainder should be 0, right? We're getting how modulo works. I'll put some spaces between things. So the year modulo 4 should be divided by 0. And that year should not be divisible by 100, should not give us a remainder of 0, right? Because we don't want it to be divisible by 100. If it's divisible by 100, our modulus would be 0 because there's no remainder. Or 400. And now I'm going to put some brackets around this whole thing. And I'm going to open it up big. So we're doing something here that I would highly advise against and I normally don't do, which is having very long lines of code. Back in the day, monitors could only show us 80 characters wide. So it's kind of a standard convention to wrap your text between 80 and 120 characters. I'm not doing it here because I've been lazy, but it's a stylistic guide that you should be aware of. So just to reiterate what this means, our length of February is at least 28 days, plus some number if it's a leap year, so that y is equal to y is divisible by 4, and y is not divisible by 100 or 400. Why does this happen? Because all of our logic comes down to an output. So in C, 0 is false, 1 is true in this sense. And so if something is true, if our logical statement evaluates to true, it means it evaluates to 1. So basically what we're saying here is 28 plus 1, if that's true, or 28 plus 0, if that's false. Does that make sense? Got a question here, yeah.
The year is divisible by 400. It's leap year equivalent is divisible by 100.
Is that the case? It is, except when it's divisible by 400. Thank you. I don't know my leap year logic. All right. So now we know our length of February. And now we can go into our print statement and instead say, print out the number of days in this current Feb as length of Feb. So let's save it. Let's go back. Let's run months check. And now let's put in this year. I don't know if this is a leap year. This is not a leap year, I don't think. February was only 28 days this year. And it shows up. February is only 28 days. Can anyone give me a leap year? 2024. Let's see if it works. 29 days. Okay. So with that, we've now got a program that tells us the months. Okay. So with that being said, what if I want to know how many days we are into the year instead? I don't want to just tell me how many months, how many days we are into this month. I don't want to tell me how many days are in this month. I want to know starting on January 1st, how many days it's been, because I know there's 365 days in the year and I know that 12 weeks of this is school and I want to know if I'm supposed to be doing school stuff. Okay. So how can we do this? How can we extend the existing program that we have that tells us how many days are in a month for any given year to tell us how many days it has currently been this year? Anyone have any ideas? How would you count it? If it's January 1st, how many days into the year has it been? 1. Okay. And if it's February 1st, how many days of the year has it been? Sorry, what was that, everyone? 32. How do we know that it's 32? 31 plus 1. We know January's finished, and January had 31 days, and then we added 1 extra. So can we extend that and think about how can we create a program that for itself will tell us how many days we are into the year? Well, maybe we can do exactly what we just did here. We can think about how many months have passed and add to that just the number of days in this month that it's been, right? So in order to do that, we're going to need to introduce a concept called loops. How many people have heard of loops? You guys might have seen these, for loops in Python. Okay. So loops are a process that allows us to iterate through types of code that helps us to algorithmically or kind of procedurally allow the computer to do some kind of information. Specifically, we're going to be taking a look right now at something called for loops. For loops, for those of you who haven't seen it, have 3 things that it kind of needs. It needs an initialization. We need to tell it where to start counting from, what its state is at the beginning. It needs a condition, or what we call a guard, basically telling us what to check to see if this loop should continue running. And it needs an update, something to tell us how we're incrementing time, how we're incrementing things. And so because of that, a good for loop runs a finite number of times if it is written correctly and you are actually changing things properly. So with that in mind, let's go back and see if we can fix this code to make it actually count our number of days. So if this is the process that we want to know what month it is, and then we're going to add up all the days from the previous months, and we're going to then add the days to this, well, first we're going to need to take in a day, right? So now it's not just that we need a month and a year, we need a day, month, and year. So let's add an extra one here. And we need our day in there. And now instead of it being checking for if there's been 2 inputs, we need to check if there's been 3 inputs. Okay, so we need to start a summation, right? We need to start counting from this day, how many days do we keep adding to it? So let's make what we call a temporary variable here, but for us, it'll just be a variable in our program, something to hold that sum. So in this, we have our length of February. Let's also have, this is bad practice, I apologize, I'm putting variables everywhere, but you will see in your textbook, you want to introduce variables right before you're about to use them. So that way, you, as a reader looking at your code, you understand when it's relevant, what that information is. So I'm gonna do one called day sum, because we're summing how many days there's been. That seems literate, that seems reasonable if you were reading this after. So we know that day sum should at least be the current number of days, right? Because we've done this many days, we don't need to count it past. If today is the 3rd, day sum should start at +3, right? That seems reasonable. We already know that number right off the top. So how do we actually go through and check for months? Well, what we're going to need to do is we are going to need to iterate, which is a fancy word to mean step through one step at a time through the months and add the number of days. Okay, so here's where our concept of the for loop comes in. So now we're going to start a counter. So I'm going to do this in one way that I'm used to doing it in. You might see it be done in other ways, which is I'm going to create a temporary variable that's just going to exist inside that for loop. I'm going to call it I. That's my counter. For int I equals 0, that doesn't make sense. For int I equals 1. So we're going to have a counter that starts at 1, and this is the month that we're counting from. Okay? If the month that we are currently counting is less than the month that we have inputted in. So that means if we've inputted in March, is the counter looking at January and February? If we've inputted in September, is it looking at January, February, March, April, May, June, July, August, September, October? All of those kind of things. So if that counter is less than that, we're going to keep running. And otherwise, we are going to increment the counter at the end of each loop. That is this I++, our post increment. It is the highest precedence operator. It will happen before other things if it is in the same line of code. So just to reiterate, our initialization, int I, starting at 1, our guard or our condition, checking that it's less than the month, and our updater. Now let's start doing actual processing inside of it. So what are we checking? We're checking firstly, if the month is February, we want to add to it that length of Feb we just calculated, that number of if it's a leap year, that 28 or 29, right? So we can actually take our old code that just printed it out and stick it inside. I apologize, we're just gonna make that a little prettier. So now instead of if that month we put in, we want to see if the current one we are looking at, right? So if I is equal to any of those numbers, we want to add 30 days to our sum. So day sum plus equal 30, which means we are going to take day sum and add 30 to its existing number. The equivalent way we could do this is to say day sum is equal to day sum plus 30. But this is a shorthand. Else, if the number is 2, so it's February, we want to instead add to day sum that length of Feb variable we just created that tells us if it's a leap year. Otherwise, we want to add 31. Right? So that looks like it should tell us how many days into the year we are. And now let's print that out. So we're going to, at the end of it all, printf, we are some number of days into the year. And that number is going to be day sum. Okay. We got a question. Oh, yeah. Ah, beautiful. Thank you. The joys of live coding. All right. Everyone, are we ready for a moment of truth? Let's compile it. I've got no errors. Let's run it through. We need a date, month, year. I have another typo in the printf statement, it looks like. Let's put in today. What's today's date? The 12th? 12th? So 12/03/2025. We are 71 days into the year. That sound right? January, February, that's 31, 28. Somebody who does math better than me, please check that. You know what? Why don't we check an easier one that I can count? Why don't we check Feb first? Because we know that one. We got an answer here is 32. So 01/02/2025, 32. Okay. That works. All right. With that, there's one other type of loop that we're going to talk about today that we can run through an example of another time. But just for your brains to kind of put something in your head, you may have heard of something called a while loop. So a while loop is one where it is not constantly incrementing a singular counter. It's really just checking a condition. That condition needs to be initialized somewhere else prior to this, and it should be changed inside the while loop. Otherwise, you run into a lot of issues, like things running forever. So the other option I would like to talk with you about before we kind of get started with this is the idea of a do while loop. How many people have seen this, a do while? Okay, not many. How many people have seen a while loop though, or have heard of a while loop? All right, okay, many more, beautiful. So the difference between a while loop and a do while loop is how many times it will increment or it will run originally. So a while loop, if the condition is false by the time we reach the loop, it's never going to run. It will not do it. However, a do while loop will run all of the code once before checking that while condition. For most of your code, you are only going to really be using while loops. There are specific occasions where you might use a do while loop, one of which I will show you right now because I do have it pre-prepped and I don't have time to kind of have us come up with it from scratch, is if we're making a guessing game. So let me move into my prepped folder, and I have code called secret number. Let's see, GCC, secret number, secret num. And so let's take a look really quick at the secret number code. So has anyone played the Akinator games? Yeah, how many people have seen this before? It's a guessing game where basically you have something in your head and the computer asks you a bunch of yes or no questions to figure out what you're thinking of. Can we do something like that? Yeah, we can if we have while loops. So if, for example, we have a while loop that asks the person to guess a number. And with that guess, we are going to check if it's higher or lower. And the reason that we're going to use a do while in this case is because we want that first guess to count, right? We want it to run through that to check, because if somebody guesses the right number right off the bat and we used a regular while loop, it wouldn't give anything to them. It would just say done. So let's see how secret number runs. So let's guess an integer. I have given us no bounds for this. So I'm going to say 12. Well, it's higher. Anyone want to give me a number higher than 12? 32? Lower. Higher than 12, lower than 32. Anyone want to try another? Sorry, what was that? 21. Higher. We got 2 more attempts. Higher than 21, lower than 32. 26. One more. Higher than 26, lower than 32. 30. Oh, no. Okay. So one thing we're going to take a look at in this code is what our secret number is, and these beautiful little things here called defines. So defines are a preprocessor command that basically says, take this name and make it a find and replace kind of variable. So that way you can use it across your code outside of the individual function that it's made in. So we will get to function scope in a little bit, but we will use things like these define statements and these constants up here in order to avoid having that number, our secret number, in the actual condition check. Because what happens if we want to play this game again, I don't want to have to go through the rest of my code and everywhere it says, well, is your guess less than 31? Write out a new number. If instead I write define secret number at the top, I only have to change my code up here to make a new secret number to run through the game again. And so in this way, these kind of defined preprocessors, these kind of constants really help to make code cleaner to read and easier to move through. So there's one last thing about loops that we want to talk about before I will give you all another break, because I know sitting again has been very, very difficult. We can run into a case where loops go on forever. How many people have done that, where you've written a code and it just doesn't end for some reason? Yeah, it happens all the time, because you're like, what is it doing? What is it checking? Why is it doing this? And often that's because something in our condition is not changing. What our actual loop is checking is not changing in any way to know to end it. And so that comes to the concept of a loop invariant and loop variant. So a loop invariant is a formal property of a loop that defines what is the same for every iteration of the loop from initialization through to the next one. And at the end of our loop, when the condition has changed and we've stopped our loop from running, the fact that that invariant has changed or is broken should tell us something about what's happened. So if we can think about our for loop structure, I'm just going to go back a little bit, okay? So please don't mind, I'll come back to this slide. But if we go back to our for loop structure, we have this idea of initializing a condition and an update. A really, really simple invariant. Actually, let me even go to our code so we can see it here. Our for loop structure up here, right? What is something that doesn't change between every iteration, and then when it does, it changes the state of our program? Yeah. Amazing. So just to repeat, because we didn't have a mic up there, it's that changing of I, that statement of I less than MM. So in our for loops, this is a very simple invariant, right? That every time the loop runs, I should always be less than the month that we're looking for, that MM. And that when I is not less than that, when it's equal to or greater than, the loop is done. It should be over. And that tells us something about logically where we are in the flow of the program. Figuring out the loop invariant can be tricky at times. And especially as you write bigger programs where you're getting into objects and data structures and other things, sometimes the elements that are invariant in the loop or not changing in the loop are actually bigger than just the condition itself. Sometimes it's information about the state of the problem. Sometimes it's information about the larger concepts about what's going on in the program. But this is a concept that is very important to start to understand, especially for later on when we get to analyzing the runtime of these programs, because when you know the loop invariant, you can predict how many times something is going to have to run. You saw this in your fat.rat example when you were looking at, okay, well, how many times does this have to run in general? How many times would these things have to run? Okay. So with that, I think that it's time we take a wee break. So we're going to take a break for 5 minutes again. And I will see you all back here at 12:15. And we are going to talk about functions. Functions, functions, functions. Okay? Are we ready to come back? Are we ready to be back? Are we all ready to sit down and have a fun time? Okay. We are going to put all of this information together as we learn about functions. Okay? So, really quickly, we are going to see, can we tell if something is a prime number? So what do we know about prime numbers? Anyone remember anything about prime numbers? We're going to actually get in the middle here. Can I get you a mic? I don't know if we have. Actually, not Alex. We've got someone in a hoodie back there. If somebody could please pass that mic back. Back 2 rows, please. 3 rows. Amazing. Can I get your name?
My name is Ming.
Amazing.
So a prime number is only divisible by 1 and itself.
So a prime number is only divisible by 1 and itself. Amazing. Okay, so what can we do to figure out if something's a prime number? Can we make code to do that? Let's start up, shall we? So let's once again start our new C file. We can all see this. I'm going to include my standard IO because I know I'm going to be taking in information, right? And I know that I'm going to need my initial main function. Okay. So I'm going to save this and we're going to call it starting primes.c, just as a place to start. Okay. So if I want to check if something is a prime number, let's start. What do I need to do with my code? I need to first take in a number, right? From the user. Okay. If I need to take in a number from the user, what do I need to check if something is a prime? If it's a prime number is only divisible by 1 and itself. So, what are some prime numbers that we know off the top of our head? Anyone have any? 7's a prime number, boom. So let's go some prime number examples. 7's a prime number. Anyone else got any other prime numbers for me? 2. 2 is a prime number. 1, right? No. What's another prime number? 3, 5. Okay. So while 1 is debatably a prime number, I'm going to do a little cheating here for computing purposes. 0 and 1 are going to count. Shh. Don't tell the mathematicians. I told you I'm not a mathematician. I'm a software engineer. I promise you I can do math. But for ease of coding at the moment, we're going to make sure that we do it just a little bit this way. Okay. So what do we do when we get in a number? We know that after we get in a number, we want to check its divisor, right? Check if it is divisible by what? What can make the factors of a number? If I have the number 7 and I want to check if it's prime, how do I check that it's prime? I'm going to go with, let's see. Can I please get, I'm just going to call on people randomly. May I get the microphone, please? Oh, actually, we've got a guest in the middle there who hasn't answered before. So I'm going to hand this through. Could you please hand this down? And can I get your name, please?
Yeah. All right. So my name is Jamu. So to check if a number is prime, all we can do is we can do like a while loop or a for loop that checks if a number modulo an integer from 1 up till itself is 0.
We can do that. That's right. We can check. So what Jamu said there was we can have a for loop that checks if there's any remainder between the, sorry, what was that last bit you said?
Yeah, so we can use like a for loop or a while loop to check if the number modulo each of the integers up until itself is 0.
All right, so I'm going to ask you to keep the mic. I'm just going to write in right now our basic print statements and scan statements, and I'm going to ask you to tell me what that for loop should look like, okay? And I'll type it out for you here at the computer. So printf, please put in a number, let's do a whole number, just so that way we are constraining our users. And we're going to scanf, oh, I'm missing something. I'm missing first an integer that we're going to call n to be our number. So scanf is going to be expecting an integer called n. All right, so we have our number n in from the user. Could I please get you to explain our for loop that you're talking about?
Yeah, so if we look at the for loop, essentially, I think we're looking at 3 conditions.
Mm-hmm.
So you have the initialization, the condition, and the update. So for initialization, we can start from 2 because 1's kind of pointless, yeah, because the number modulo 1 is always 0. So we start from 2, and the condition we're checking is if the number modulo, I in this case is equal to 0.
Sorry, what was that? I starting at 0?
So we're checking if the number modulo the counter is equal to 0.
So you're saying I starts at 2, and we're saying the number modulo I equals 0.
Yeah.
Is that what we're saying?
Yeah.
So what we're saying there is that the number we've put in divided by the current counter, which is starting at 2, if there is no remainder, then what?
Then if there's no remainder, then you can stop the code. Otherwise, you increment by 1.
Okay, so what do we know from here? If there's no remainder, then it is we found a factor, so it's not prime. But can we tell from this if it's prime? What are we going to do? We're going to say, ooh, if this loop breaks, we're going to say it's prime then? Is that kind of your idea for it?
Yeah, that's what I was thinking. Yeah.
Okay, so we're saying if this loop runs, and every time it runs, every time it's incremented, once the minute we find a 0, we're going to say printf, the number is not prime. And we'll say a factor is whatever currently I is. So we're gonna check. We're gonna see if this runs and how this works, okay? And I will throw in a little statement here to kind of help us with controlling for loops. Because in theory, what happens if we're checking here for that condition to be true, right? So that middle condition is saying, while that is true, keep running. But we don't want it to keep running when that's true. We want it to actually stop when that's true, right? So what we're going to need to do instead is to think about a way to tell our for loops how to do that. I'm going to get to it in a second, but can we take a step back from for loops and let's think about it as an if statement. Let's think about it with that basic control structure, and then we will come to how to make it nice and pretty with for loops in a minute. So I'm going to do a different type of comment than you might have seen, which is a block comment, where instead you go /*, and that will put it there. So let's start with a really, really broken, ugly program. So if n, our number, is less than 2, let's just consider it prime, right? That's what we said here. I know it's not true, but the number is prime. Else, what's going to happen here? Now let's introduce our for loop. Let's introduce the concept for int I, which will be, I shall call it divisor, just to make it clear what this is. This is the number we are dividing by. And we're going to start with the divisor equal to 2, just like you suggested, because we know that if it's less than 2, it's fine. And now let's think about a different property. We're going to go if the divisor multiplied by the divisor, so the divisor squared, is less than or equal to n, then we're going to increase the divisor. Why are we doing this? This looks weird, right? How many people kind of get where I'm going with this already? A little bit, maybe not everyone. So let me walk through and explain it. If I'm checking for factors, right? And I'm saying that a factor has to be a smaller number than the number I'm already looking for, and I'm going one at a time to check through, then a factor can't be more than the square root of that n. Because if that's the case, we know that if there's a square root of n, then it has a factor, right? So anything below that square root is what we're actually needing to check. So this is one of those cases where our math knowledge is going to help us be a little lazy with programming. And really lazy here means efficient. We don't need to check if I have 36, what's the square root of 36? 6, right? So I don't need to check past 6. I don't need to write a loop that's going to run all the way up to 35. I know that if there is a square root, if that exists, I can stop there because a square root shows me that there's a factor. Make sense? We're following along? Okay, so that's where we're going to change your for loop just a little bit because we do want to make that comparison of the modulo comparison to see if there's a remainder, but we just didn't know how to do that in the condition. We want to make sure that the condition is telling us the invariant of the loop, something that must be true every time. And we know that true every time, we want to go only up to the square root of our number. Now we can actually check our conditions here. So for this, now we're going to say if n modulo the divisor is equal to 0, which means that our number divided by this has no remainder, then it's prime, right? Or then it's not prime. It has a factor. Printf, the number is not prime. Okay? Now, instead, if the number has a remainder, then it means that it might be prime, right? This is a little ugly, isn't it? We don't like ugly code around here. And in fact, there's something a little weird when I write it like this. And I wrote it like this for a reason. One, because it's ugly, and I wanted you to take a look at ugly code to lead us into our next step. But two, because here, what happens with an if statement in a for loop? So if the divisor is, if n modulo the divisor is equal to 0, and we know the number is not prime, but our condition is checking that the divisor is just less than the square root of n, we're just going to keep running, right? So we need a way to tell the computer, we're done, finito. We do not need to look further than this. We need to break out of our loop. And C gives us a very handy little keyword called break to do that. When we type break in a loop, it says, get me out of this loop. I'm moving up one level. We're good here. Okay. So now let's check this out. And I'm going to, did I already write return 0 at the bottom? I did. Okay. So let's save primes and see if it runs. So gcc primes.c primes. Oh, I'm in the wrong directory. Anyone remember how to change directory? CD, beautiful. And we're going to use the shorthand of 2 dots to mean go up 1. Let's check here. Oh, there's our lovely primes. So let's go through and primes. So let's put in a whole number. Can somebody give me a whole number? Shout it out. 20. 20 is not prime. Okay, that seems to work. Can somebody give me another number, one that they think is prime? Sorry, what? 19. Number is prime, number is prime, number is prime. Oh no, why do we have that? Does anyone remember what we're missing? We're stuck in the for loop. Excellent. Good job. Okay. Now, obviously we can do it nicer. We can have an else statement, but the problem, what would the problem be with having an else statement is the same as having this if statement is we still need that break. We still need it to say, we don't need you to run this, right? And the other thing is everything in a for loop runs every time. So that means it's going to constantly print for everyone we check if it doesn't think that it's, if it thinks that it's prime. Does that make sense? Do we want to try it out and see what I mean by that? Let's try it out and see what I mean by that, of why did we do it as a separate if statement instead? If instead I went else, because obviously if it's not prime, the else should be it's prime, but that's not always true when we're checking. Even if I leave a break, it's just going to break. So this is the wrong code, and I'm showing this to you because it is wrong. Please do not copy this and think that it is right. This is an example to show you what can go wrong when we don't think it all the way through. So let's go through 19 again, right? Or let's go through 20 again, a number we know is not prime, right? And let's go through, have I done this right? Yeah. Let's go through 19 again. The number is prime. What if we have to go all the way up to 100? No, it's because I put in the break statement. All right, we're good. There's a lot going on in this code, right? And in fact, as you will see, our main statements are starting to get really bogged down with stuff to do. And so one way we can deal with this is by outsourcing certain jobs that are repetitive or able to be handled independently to other functions. So what's a function? A function is basically code that accomplishes some kind of job. It works together with all the other functions and main functions to make things go well. It makes our code cleaner and more modularized so that way we can reuse it. Because like I said, I'm a lazy programmer. I don't want to have to type out the same things over and over again. So we're going to go over some basic function definition, and then I will run through how to make a nicer function version of is prime, and then I think we might be done for today because I'm looking at the time and it is 12:35. So a function is called by its caller, and we call the function a call, the function that is called a callee. So we can have the idea of our main function, which is our number one that we have in every program in C that we're going to run. If it wants some help, it's going to be the caller and call another function that exists and say, hey, here's some information. I need you to do this job for me. I need you to handle this. And then that function, the callee, is going to work on the problem with the information that we passed to it until it runs out of code or it hits a return statement in the code. That's what lets it know it's done. That's what helps it to understand I have solved the problem that my original caller told me about, and I am ready to pass that information back. The callee then returns the output value to the caller and then throws out all her work. She's like, I am done this. I don't need to know the rest of these variables. I don't need to know the intermediate steps. I just needed you to give me some input, and I gave you my output, and I'm done here. So that's really important to understand that when our functions get called, we are passing through to them information. They get control of our project. They get control of the code. They will run through first. And then once they're done and pass something back to its original caller, that caller is now going to retake control of the project and continue on from there. This is really important when we're understanding the control flow of logic in our programs, as well as understanding what we meant when we said it's an imperative language, right? Our main statement, our main function is doing every statement in order. So even that call is happening in order. If at some point we say, call this, printf is a function that we call a lot in this course and a lot in our examples. We're saying for a second, hand over control to the printf statement, let it do its thing, and then when we come back, we'll go to the next statement. An important thing with that to understand is that functions can be chained together. So that way, if we call one function and say, hey, can you handle this problem for us? And they go, okay, I'm working on this problem. And then function one goes, oh my gosh, actually, I found a new problem. I'm going to hand it off to my partner function two to look at. And function two is going to go, okay, I'll take control now. I will do this part. Oh my gosh, here's another part. I'm going to call function three to take control of this right now. And then they'll chain together their inputs. And then once the last function who gets called has their output, they will return that all the way back up the chain to finish off their work until they get all the way back to that main function. Does that make sense? Everyone can see where we're kind of going with this kind of game of telephone where a function calls a function and that function might call another function, and then we're going to get all the way back. Okay. So that's conceptually what functions are. They are something to help us code and do smaller jobs. They're something that makes our code cleaner and reusable, and they're something that can work together. Now, how do we actually write functions? So every function has something called the function signature. This is basically their handle, their name, their user tag, whatever. But they all follow a very similar format in C. So the first thing that a function has to have is its return type. That is telling us what output the function is going to have, or what type of output the function is going to have. So this is where you will see in our main functions, we have int main. If we scroll all the way up, we have int main. Our main function is going to be returning an integer value, and that's why we have this little return 0 here at the bottom. Because we're saying every function needs to return something. Our main function is returning an integer. Okay. Oh, I had it up here. After the return type, we have the actual function's name, its handle, what it's called. So in our case, it might be main. As we're making other functions, we're going to give them fancier names or more descriptive names to explain what they're doing. And then we have inside the brackets beside the function any arguments that it's going to take in. Those are those variables that it's being passed to by the computer or by another function that it's going to then use to do its job. So we got into that question of what are these in the middle here? Those are arguments that our main function actually takes in from the shell 2 arguments, an integer called argc, which is the number of arguments that it's going to get, and then a character array called argv, which is the actual set of arguments that we're going to get here. You don't need to know that right now. this is just some context in case you're sitting here going, why won't she explain what argc and argv are? Why do we have to type it every time? It's just the inputs that go into the main function. Okay, so with that being said, let's make a nicer is prime. So I am going to do most of this coding, but I will ask for help from you for a little bit just to keep us going with time. So I'm going to actually add a couple of different libraries here to make this job a little easier for us. All a library is a collection of functions that someone else has written that we can use. So that way we don't have to keep writing the same thing over and over again. How many of you have been in this kind of course where you're like, we are all writing a prime function. Why can't I just use someone else's prime function? Right? It sucks. No one wants to reinvent the wheel. We ask you to do these things because it's good practice to know how to do it. But once you've been doing it enough, just use someone else's. So that's what we're going to do. I'm going to use someone else's code for other things. So I'm going to use that standard library. That's just going to allow us to exit if we have any checking issues. You call that exit function. And I'm going to include another one called standard bool, because Boolean variables are not a primitive type in C. They are primitives, which means they are involved or in part of the language in other languages, but not in C. Bools don't exist. That's why you saw a lot of things evaluate to 0 or 1. However, there is a lovely library called standard bool that allows you to use Booleans. So feel free to use that if you would like. Now, it would be really, really nice if after taking in this prime number, we just had a way to go, is it prime, right? Is there a function that we would just go, hey, we have our number n. If is prime, then just print it's a prime. Else, the number is not prime. Wouldn't that be so much prettier? Wouldn't that be so much neater to write? Right? This is what functions are going to do for us. So, all right. So now we want to write this is prime function. So we want it to be Boolean because we know that the if statement is going to take in and evaluate to either true or false. So our output of is prime should be either true or false. That's Boolean. So we know our output type is Boolean, and we know the name we want to give it is prime. And we know that it's going to need to take in something. What's it going to need to take in? What are we checking if it's a prime? Feel free to yell it out. The integer, right? Whatever num. So it's an int n. So now here's something a little funky about C. C is a language that because we know we're going to be calling this function, we need to know that function's name, right? And specifically our main function, if we go back to our little chart here of like people's names, if I don't know the name of the function to call, who am I going to call, right? We don't know. We don't know what happens. And so C actually needs you to put the name of the functions that you're going to create or call up at the top of your document before your main file or before your main function. The reason being is so that way the main function knows who to call. It's giving you your phone book of names. Now, there's two ways you can do this. The first way is kind of the one most people learn and try, which is you can put the whole function implementation up top. You can just say, bool is prime, and I'm going to write the code for it up here, and it's going to exist before my main function. That'll work. However, it might also be really, really frustrating to be like, I wrote my main function. I don't want to have to keep scrolling up to know what I'm putting in. I don't know I'm going to need it beforehand. So what if I want to write my is prime below my main function? Well, we can do something called function prototyping, where we tell the main function the name, and we say, you don't need to know the details of how it's going to do this thing yet. You just need to know who to call. You just need to know the function's prototype. And what that means is we put that same function signature up top, and we just put a semicolon after it. And that basically says, know that this exists, and we'll tell you how it works later. Make sense? Prototype means we can do it after. If you don't want to use a prototype, you can put your function all the way up at the top, but that's also a sign of stinky code, of kind of just like, it's not very elegant, it's not very pretty. And it also doesn't help when we want to eventually make a lot of functions where we're having to scroll through really big files. Okay. So now let's do our actual is prime here. So now we can take that whole idea of if we have our divisor, right? And if n is less than 2, we're going to say immediately that it's true, that it is prime. And we can here return, or yeah. We're going to return true, right? If it's less than 2, we're saying it is prime. Else, for our divisor equal to 2, divisor times divisor. So this is the exact same stuff we had going before, right? Is less than n. Checking each factor. If n by the divisor equals 0, then we're going to return false, which this is going to mean not prime. Otherwise, and what did we need? We needed a break statement, right? Else. All right. Moment of truth. So now we are just checking if our function works. We've written a function that seemed to work before when it was in main. We are now checking if this function works and will tell us if something is prime or not. And we are going to primes. We are going to compile primes again. I'm going to change the output name to primes fun because it uses functions. It looks like it compiled fine. So let's put in a whole number. Anyone? Got a number for me? 5. The number is prime. Okay, let's try prime's function again. Anyone else? 1 more time? 1. The number is prime. The mathematicians are going to be very unhappy with me, but like I said, I'm a software engineer. I could be bad at math. Okay, 1 more time. Anyone? 73. The number is prime. Okay, let's pick a number that's not prime. Something we know, like 20. The number is not prime, so it works. Our function went and did its job and helped our main function be a lot cleaner and easier to read and do its work a lot more efficiently. So this is what we were saying, but either the function signature or the function itself must appear in the code before you use it because we need to know who to call. And like we said, we've been using functions the whole time. Printf, scanf, we're borrowing from our standard input-output library. When we want to use things like the exit code, etc., we're borrowing that from standard lib.h. So, as we kind of wrap up for today, we talked a little bit about the joy of libraries, the joy of these collections of C functions that are compiled elsewhere and written elsewhere that we just get to use. There are lots of them, and as your programs get bigger, you are going to see many, many more. But there's a lot of functions we also use that we're not linking separately. We don't have to go out of our way to download a separate library or link it to our other code. Well, That's what the C standard library is. You might have heard me refer to the standard library. That is the built-in set of libraries that you can access with just those header files. Basically, everyone got together and went, we're using these functions all the time. We don't want to have to keep downloading libraries and linking them to our code and doing all that stuff. Can you just bake this in so that way the C compiler knows these ones exist? And that's what we have done here with those things. So our character processing, file creation, a lot of our basic stuff is part of those standard libraries. Otherwise, if you are making your own library, you will need to actually link it to your program. So what that means is going through and putting a -L and then having the library name beside it. I will go over that at the beginning of next lecture because we are running out of a little time. But I just want to leave you in our last minutes with a little puzzle to think about for next time. Could I get a volunteer, please, to the front to play a Wii game? Anyone? In the back, on the white shirt. Let's go. Round of applause. I don't have another mic down here, but what is your name?
I'm Chi.
Chi? Chi, lovely to see you. And I'm going to give you a little puzzle. So I have here 3 pegs and some rings on them. How many of you guys have seen a game like this before? Okay, a couple of you. Excellent, excellent. So I'm going to need you to take these rings and move them over here to the last peg. However, there are some rules. You can only move 1 ring at a time, so that's fine. And you cannot put a bigger ring on top of a smaller ring. So you have to make sure if you're putting rings in that the big rings are on the bottom and the small rings are on the top if they're stacking together. Okay. So before you go, before I ask you to do that, I'm going to pull up a little stopwatch timer. Okay? We're going to see how fast you think you can go with it. All right, do you want to take a guess?
I guess 3 minutes.
3 minutes? 3 minutes is our guess here. Okay. And does anyone want to take a guess how many steps or moves it's going to take our lovely Chi here to do? Yeah. 31? You think it's a minimum of 31? Okay. All right. So in our last 2 minutes of class, everyone, I'm going to get one more round of applause for Chi, please. And I'm going to start our timer. Ready, set, go. We're at 3 steps. Somebody count steps for me, please. It's 3, 4. Oh, we can't do that. It's harder than it looks. I'm really bad at it. Do you want to stop? Do you want to? Oh, you're doing it?
I quit.
You quit? Okay. Round of applause for Chi. Does anyone else want to come up and try? We're going to get somebody who hasn't volunteered yet. Somebody hasn't volunteered yet. Want to give it a go? We got some volunteers. We got some volunteers already. Okay. I'm going to go with in the hoodie, in the black hoodie. Do you want to try? Yeah. 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 Do you want to try? You. Glasses. Yeah. Okay. Thank you so much, Chi. All right. This problem is called the Tower of Hanoi or the Tower of Brahma. And next week, we now have all of the pieces to start looking at how do we solve this problem programmatically. Amazing. All right. All right. Name last time for everyone in the class. I know you've answered before.
Ming.
Ming?
Ming.
All right, Ming. And what's your prediction? How long do you think you'll take?
3 minutes.
3 minutes? Okay. Are you ready to go? Ready? Everyone, round of applause for Ming. Okay. Ready, set, go. Come on, Ming. Ming, Ming. Can I get a chant going? Ming, 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 Ming. Wow, we're not a big chanting group, are we?
To here, right?
Yep, to there. All right, it is 12:57, so you are all free to go. We are just going to finish up here, but thank you so much for coming to week 2 of Foundations of Algorithms. I'm really looking forward to seeing you all next week where I'll be handling lecture again. Ming, 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 Ming. You're doing it. You're doing it. You're doing so well. Oh no, we've psyched you out. You're doing great. You're doing great.